Hello, my name is Ariel Martinez, and this is Lab 5, Explore Your Adventure. For this lab, I chose to analyze the motion of a ball attached to the bottom of a falling slinky. So today, I'll talk about a small introduction to the lab. I'll describe the lab procedure, my tracker setup, the initial conditions for my code, how the initial conditions for my code were generated. I'll describe the code that I wrote to model this motion, as well as the graph this code produced, and then analyze what all this information means. So as a small introduction, for this lab we are examining the motion of a ball attached to a slinky as the slinky is dropped from rest with a ball attached beneath it. So since the ball is attached to the bottom of the slinky, the two forces acting on this ball are the force of gravity pointing downward and the force of the spring pointing up. So the force of spring is this equation written here, where the force of spring is equal to negative k minus L naught times L hat, and the force of gravity is mg, and the net force acting on this ball is just gravity plus spring. Using Newton's second law, we can find the velocity and position of this ball as time progresses using the velocity update formula and the position update formula. So for this lab, what I did is I found a video on YouTube of a man holding a slinky in a ball and dropping the slinky, and then I uploaded this video of this ball slinky system to tracker, set up the initial conditions and plotted the position over time data, and then using the initial conditions generated from this tracker model, I created a computational model of this motion using VPython, plotting the y position over time. And then I compared and observed the data from the computational model and the real observed data, and analyzed any potential reasons for difference between the two. So here is my tracker setup. This is the video that I found on YouTube. We see the ball dropping in the bottom of the screen, and on the right we have the x and y position time data over time. The only position time data that I actually used for my model was the y position data, as you can see in the top graph over there. The y position of the ball as time progresses. So here are my initial conditions for the code. So the ball of the mass was the ball was a standard tennis ball, so I just looked up what the mass of this ball is. The initial positions shown here were the initial position of the ball as shown on the tracker simulation. The initial velocity of the ball was 0 because the ball started at rest. And then in order to calculate the spring constant, I noticed that at the beginning of the video, the ball was at rest as the slinky was held at the top, meaning that the force of gravity, the magnitude of the force of gravity and the force of spring were equal. So I set them equal to each other, and knowing the mass and I measured the length of the slinky and while it was stretched. So knowing that information, I was able to calculate the spring constant, which is what is shown here, and also the relaxed length of the spring. I was able to calculate it by just looking at the video and comparing that to the height of the man, which was known. So I got that it was 0.25 meters, and then through that information I was able to calculate the L hat and the magnitude of the length of the spring of the slinky. So here's my code, the calculation loop. So first I calculate the force of gravity, then I calculate the force of the spring, then I calculate the net force. Once I have the net force, I can update the velocity, then update the position, then update the length of the spring, meaning the new position of the ball, and then based on the new position, calculate the new size of the slinky, and then I plotted all this information, which is going to be shown on the next slide. This model graph, this here shows the y position of the ball as time progresses. We can see that the ball drops over time, so it starts first a little bit stationary until the slinky falls to the bottom. Once the slinky falls all the way to the bottom and that force of the spring is no longer felt, it dissipates all the way down, then the ball starts dropping, and that's what we can see here, the y position of the ball dropping over time. So analyzing what this means, so why doesn't the ball drop until the end? So if we analyze the video closely, we can see that the ball stays stationary until the moment that the top of the slinky falls all the way down and collapses on top of the ball. And the reason this is true is because the only forces acting on the ball are the force of gravity pointing down and the force of the spring, the force of the spring of the slinky pointing up. So when the top of the slinky is dropped, the bottom is still attached to the ball, which has not received the message that the slinky dropped. Only when that force of the spring dissipates, when the slinky reaches the ball and collapses on top of the ball, does the force of gravity become the only force acting on the ball, which forces it to drop towards the ground. So that's why we can notice the small lag of the ball dropping at the beginning, where we saw that it stayed stationary because the slinky hadn't dropped on it yet. So it still had the force of spring up and the force of gravity down. So only once it reaches the ball, that force of spring is no longer constant, is the only force acting on the ball, the force of gravity pointing downward, which is when the ball starts moving down, as can be seen by the graph.